My name is Rafael.
My name is Ed Stubblefield.
My name is Edward.
I'm Damasio.
And our presentation is on the examination of bariumstannate for power electronics. So semiconductors have allowed power electronics to become smaller, faster, and more reliable. Silicon is a semiconductor material that is most widely used throughout the world because of its low occurrence of defects, and it can be fabricated easily. However, silicon has improvements that are saturated. Alternatives being researched are gallium nitride, silicon carbide, and bariumstannate. The energy required for current to flow is referred to as band gap. Metal has no band gap, which allows current to flow freely, while insulator has a huge band gap, which offers large resistance. Semiconductors fall between a conductor and an insulator, which has a medium-sized band gap. And semiconductors are special because we can control the way current passes through them like a switch. And bariumstannate is a wide bandgap semiconductor with high electron conductivity.
Here we see bariumstannate compared to a well-known semiconductor known as silicon, as everybody knows. For the bandgap energy required for silicon, as you can see on the left, requires about 1.1 electronvolts. On the other hand, bariumstannate requires about 3 times as much. So what does this mean really? It means that we can operate with bariumstannate higher voltages. We can also operate at higher temperatures without fading. So our goals for our project included us to study this material for power electronics applications. We also understood the growth mechanisms required to grow this material on the MBE machine, or molecular beam epitaxy. And next, we study the quality and electrical properties of this material using 3 known tools: atomic force microscopy, the Hall measurement, and X-ray diffractions, well-known tools.
So as Eduardo mentioned, we're talking about thin film growth using molecular beam epitaxy, or MBE. MBE is one of the various ways that thin films can be grown, but it is the best way to grow highly ordered and contaminant-free films. On the left here, you can see the entire MBE system with a human for scale. And we're going to be focusing primarily on the growth chamber here in the center. On the right, you can see what takes place magnified inside the growth chamber. The epitaxial layer the layers are comprised of the components of bariumstannate, and they land on a substrate, condense, and layer by layer or epitaxially form within the film. On this slide, you can see in more detail what happens inside the growth chamber. All of this is taking place inside a ultra-high vacuum environment, whereby all the air is sucked out of the growth chamber, and along with it, the contaminants. But before that can happen, we need to choose a substrate with a similar lattice pattern to bariumstannate, or the thin film that you want to grow. And once it's inside the growth chamber, the substrate is heated along with the diffusion cells. The beams travel through the vacuum with the vaporized materials, land on the substrate, and grow epitaxially or layer by layer.
So after we have grown our thin film using MBE, we wanted to test the surface quality of this using atomic force microscopy, or AMM for short. The way this machine works, it has 3 main components. First is a cantilever with a sharp tip at the end. We shine a laser on top of this tip. Then it gets deflected into a photosensitive diode. Now, as it scans across the surface, this cantilever then gets deflected at bands. Any halos or values that it picks up then changes the deflection of the laser and is picked up by the photosensitive diode. And in the end, we will get an image that looks like that. As you can see here from this image, it's a 10 by 10 micrometer area, pretty small. Also, as you can tell from the picture, it is uniformly colored, the same gray color, which means our surface is smooth, great for research use. If it comes out blotchy or uneven in color, it means that our surface is rough, so we won't want that. The white specks that you see on the area are just dust particles that made their way onto our sample as it was being transferred onto the machine.
And so after using AFM, we wanted to test the quality of our raw sample, and we used X-ray diffraction to test our sample. In the process of XRD, we focused X-ray beams onto our crystal film, which then were diffracted, which created diffracted X-ray beams, which are then captured by a detector, which measured the intensity and the angle of which it created our X-ray beams. And the data gathered from our X-ray diffraction, as you can see, it created a graph with our x-axis being our degree of diffraction and our y-axis being the intensity of the diffracted rays. And from our data, we gathered that bariumstannate created a single symmetrical peak, which is a good sign of bariumstannate being a good film.
So the last analysis technique we used was the Hall measurement. At this point in our research, we know the morphology of our thin film from the atomic force microscopy measurement that we took. We know that the thin film's orientation and that it's good quality from the XRD measurement that we took. But now we want to know about its electronic properties, and so we take advantage of the Hall effect for that. And this involves passing a current through the thin film and applying a perpendicular electromagnetic force to the current and the thin film. And what this creates is a Lorentz effect on the surface of the thin film, which polarizes the charged carriers, at which point we can then attach a voltmeter to the opposing sides here and here and get the electronic capability of the film. At that point, we can derive things like resistivity, carrier concentration, and electron mobility. So we did that, and the results that we got were very promising. The thin film that we studied had higher electron mobility than silicon carbide, which is widely used and kind of saturates the market right now. The downside is the carrier concentration. It's lower than we'd like it to be by 3 orders of magnitude in this particular study. But we do have a wide bandgap semiconductor with electron mobility that's higher than silicon carbide, so that's promising.
So in conclusion, we got good morphology that was verified by atomic force microscopy, and a high quality film that was verified by X-ray diffraction. Our Hall measurement showed that we got an electron mobility of 70, a carrier concentration of 5.3 e to the 15, but it could be improved through further research. So in summary, bariumstannate is a wide bandgap semiconductor with high electronic conductivity. We received promising experimental results, which we used AFM, XRD, and the Hall measurement, but further research is needed so we could apply it to future applications. And we'd like to give a special thanks to Ellie, Angel, Jens, and Jenny for showing us around the PL lab, and our mentor, Monique Goyal. Thank you for listening to our presentation, and we had a wonderful experience here at UCLB. It was 2 weeks.